So, in the last module we discussed the adiabatic temperature and the adiabatic heat transfer coefficient, and we showed that adiabatic heat transfer coefficient is the right descriptor for electronics where you have multiple heat sources influencing each other, and using a very simple IcePAK analysis without high accurate grids and so on. But this temperature you can experimentally, people have shown that adiabatic temperature is the right temperature and also measured heat transfer coefficient based on adiabatic heat transfer coefficient and shown that adiabatic heat transfer coefficient is the right descriptor. Now, we will see understand what is that we can understand from interpret from the meaning of adiabatic heat transfer coefficient. If I were to use Newton's law of cooling, which is to say that my heat transfer rate is equal to adiabatic heat transfer coefficient times the surface area times the surface temperature and the adiabatic temperature. We write that in terms of surface temperature, because for electronics our interest is to keep this fellow, if it is a junction temperature, below a certain maximum temperature. So, now we rewrite in terms of surface temperature as T adiabatic plus the heat transfer rate divided by, or the power dissipated by the device divided by the adiabatic heat transfer coefficient times the area, surface area. We add and subtract in inlet temperature, this is the incoming air temperature, then we get a definition of Ts minus Tn, T adiabat minus this, and we also add the mean temperature into this mixture, add and subtract. So, you get three terms, which is Ts minus Tin. This is the temperature rise with respect to the inlet temperature of the temperature rise of the device with respect to inlet temperature of the air that is entering the system, and this is the mean temperature minus inlet temperature, how high the mean temperature is with respect to inlet temperature, and then how high the adiabatic temperature is with respect to the mean temperature, and what is the finally my, this is my Q by HA D, which is the convective part of it. So, this is the so called the self heating part, because Q is the self heating, meaning that the Q is the heat dissipated by the power device or the silicon die, for example, or any electronic device for that matter. So, this first term, let us analyze it, which is T mean minus T inlet. What it says is that if this fraction turns out to be much bigger, if this contribution seems to be high, that means our flow rate is typically low. So, one way to increase this, because this is nothing but Q equal to m dot Cp into T mean out minus T in. T in is nothing but T mean temperature that is entering the system. So, this is T mean out, and so the only way to decrease this temperature difference is to increase mass flow rate, because the power is fixed, this is constant, and Cp is also assumed to be constant for this temperature range, which is usually 0 to 100 degrees Celsius. Cp is assumed to be constant, and you can use film temperature to obtain Cv. So, now that is what it says, that the first bracket says that if I want to keep the temperature rise of the source with respect to inlet temperature to a smaller degree, the first term says that increase my flow rate if this term happens to be higher. What about the second one? The second one says that my heat source, if they are in close proximity, this guy is higher, then I enter this guy, and if this powered off, this temperature is what will imprint on this temperature. So, then what happens is that this becomes, the adiabatic temperature becomes larger. That means, if I do not have, if this is my mean temperature, if the temperature difference between the mean temperature and this max adiabatic temperature is higher, that means I do not have sufficient mixing happening in this region. So, what do I do? Introduce, for example, one of the well known ways is to introduce a circular cylinder or a scoop or other ways of mixing air in the system. So, this mixing air decreases the adiabatic temperature. So, if we increase the mixing of air in this zone between the heat sources, then we know that the adiabatic temperature will come down. So, the adiabatic temperature should be equal to T mean if it is perfectly mixed. any difference between the two is caused by the non-homogeneity or the stratification in the temperature region. So, that mixing, if we promote using mixing promoters like cross cylinders or scoops or other vortex generating devices, then you can improve that. The last one is the self heating part, which is dependent on the heat transfer coefficient itself. The heat transfer coefficient, you know for a fact that increasing the turbulent intensity will increase the heat transfer coefficient at the cost of course pressure drop, but the heat transfer coefficient will go up by, in the case of the third term tells us about the self heating case, and the heat transfer coefficient needs to be increased to decrease this part. So, these three terms tells us a lot about the adiabatic heat transfer coefficient. So, with that we will move on and to look at what happens in the case of protruding arrays when there are multiple heat sources. Here in this scenario I have shown 6 heat sources on a substrate and air is flowing, and if it is an internal flow, then there is a solution in Case and Crawford. This comes from Case and Crawford. You can use the same idea of unheated starting length. Here the psi is a coordinate that is used here to discuss. In the previous example we discussed x naught as the starting, but we want to have a generalized discussion. So, we are going to use psi as a way to discuss the unheated starting length. Here the heat flux is applied over a small zone here, over a small zone delta x, and you have fully developed flow entering the system, and with this psi we can write the expression for energy equation, which is again linear in nature for a tube. This is for a tube. The boundary conditions will be at the center line. You are going to see temperature profile being symmetric. So, that is the radial symmetry, and then this k dt by dr at r equal to r, which is the capital R is the radius of the tube. At the wall we are imposed with a flux which is a function of x. In the unheated starting length problem we discussed, we use temperature. Here we are taking into account flux because really the heat sources tend to be flux based, and without spending lot of effort, the general solution for this is obtained, is given in Case and Crawford, is in the form, and you can write it in the form of adiabatic wall temperature itself, and you get what is called a superposition kernel function. This is given there. It is very much similar to the unheated starting length problem that we discussed for a flat plate. If it was to be adopted for a tube, and if we had arbitrarily varying wall flux, that tube solution with unheated starting length with superposition principle, we will get an integral of this form, and that is what this is. And gamma and am, they are eigenvalue constants, eigenvalues of this problem. So, for a single patch you get this T wall adiabatic equal to T in plus Q by 4 m dot Cp into Gx minus 3. If psi is equal to 0, you get the case of flux being right from the beginning is equal to constant. So, this 3-dimensional, so what we developed as an unheated starting length problem, as you can see, can be used in this case as well, and this kernel function were used by many researchers to obtain wall temperatures, adiabatic wall temperature as a function of multiple heat sources influencing a single heat source by turning on off a certain heat source, and this becomes much more easier in these days with the softwares packages like IcePAK, Flowtherm and many other softwares, where you can parameterize your domain and you get adiabatic wall temperatures as a function of all the locations and influence of all the heat sources, and you get a matrix of adiabatic wall temperatures. Once you have the matrix of adiabatic wall temperatures, then you can define heat transfer coefficients for each and every one of them. In typical design procedure, you see that power levels are not well understood in the initial stages of design. So, even if the power levels are changing, once you know the adiabatic wall temperature, as one can see using one unit power or so, you calculate it, then any increase or decrease in power levels can be easily accommodated into that matrix and calculated. But we will not go into that level of depth, but what we can see is that the unheated starting length problem can be becomes very useful even for practical situation if we take into account the arbitrarily varying wall flux or wall temperature as a means of understanding some of these things. Now, with this module we conclude the idea that adiabatic heat transfer coefficient is a critical principle that we need in terms of defining heat transfer coefficients. Now we move to the next part, which is the heat transfer enhancement. When we talk about, so far we talked about how to define heat transfer coefficient, we looked at the introduction to what is electronics, packaging and so on. Now let us look at the heat transfer enhancement. How do I define heat transfer enhancement? When will something work, when will something won't work, and it is not, there is no clear principle, but we will just look into what can be done. So, here is a, whenever we talk about a heat transfer enhancement, we typically talk in terms of heat exchangers, where the often people are looking to make it compact or making it much more, the heat transfer enhancement to be much higher, because they want to dissipate more power or reduce the pressure drop in the heat exchanger or heat sink. So, here is a situation where we talk about a heat sink. There is an airflow. This is a front view of the heat sink. Air is going into the page like this and exiting the heat sink. In the side view, you have a heat sink coming like this, and the airflow is entering and exiting. This is side inlets. The top is covered, bottom is where the heat is applied, and heat is dissipated from the base of the heat sink all the way into the fins, and the fins convey the transfer the heat to the flowing medium. So, this makes the arrangement somewhat simpler to discuss the further discussion. So, this is a calculation that I have done to obtain the situation, to compare what is the complexity involved in understanding when the heat sink, this is called a fully ducted configuration with no tip clearance, and the second configuration here is there is a small gap. This small gap is sufficient to create a lot of issues, and this bypass, because the airflow will always go, even though the flow is going to start from here, there is a gap on the top. So, the airflow starts here and goes here from a fan, and it sees there are two paths. It will take the least resistive path. Some flow will bypass the heat sink and it will go to the top. Only a limited flow will go through the bottom if the gap is large. So, you have a situation where you have pressure difference on the top and bottom. However, the pressure drop will be same, and this is if some flow will bypass and will take the least resistive path, and this will go through this. So, you can have a situation as shown here. So, what happens to the heat sink design? And the more complex arrangement is where there is bypass on the sides, on the top, and so on. So, if you see, if I had number of fins and I am interested in finding what is the way to balance this, you will see that number of fins versus thermal resistance of a heat sink, which we define as, let us say, base temperature minus the ambient air temperature. So, we define the heat sink resistance as T base minus T ambient divided by Q, the power dissipated by that device. So, this, if I were to plot in the form of resistance instead of, this is nothing but your 1 by HA type situation, or we will see why 1 by HA is not a good assumption in some cases in the upcoming slides. So, in thermal resistance is plotted as a function of number of fins. So, what happens is that as I increase the number of fins, initially the resistance is high and it starts to drop, and it comes down to a lower point when there is no bypass. This is this case, when there is no bypass, it comes down to a lower point, and then it starts to increase the resistance. Why is the heat sink resistance dropping and then increasing? But you see more dramatic effect when you have this bypass flow, when as you start adding more and more fin, and I send a certain pressure drop is fixed across it. What we are doing here is that the pressure drop across the heat sink is fixed to a constant, and as we add, this is fixed to a constant as we add more fins. So, what you see is that there is a decreasing trend and then increasing. There is a minima. Why is there an optimum or a minimum in resistance in this case? The reason primarily starts with this idea is that initially when there are very few fins, is that for a fixed pressure drop a certain mass flow rate is generated. because of the skin friction effects or form drag effects. You can calculate a certain pressure drop, and you will see that a fan of a fixed size will generate a certain pressure drop, and it will generate more flow when the resistance is least. So, it will generate more flow. So, when there is more flow, heat is dissipated from the mechanism of heat dissipation is that heat is being conducted through the fins and then convectively transferred to the moving air, that is going between the fins. So, as the air is flowing through the channels of the heat sink, now it picks up heat. But when there are fewer fins, more mass flow rate is available for fixed pressure drop constraint, and this is a very good constraint for many packages, and also for pumping power is also a good constraint, but delta pressure drop across the heat sink is a good constraint as well to deal with. So, fewer fins, as you add more fins, there is restriction being added, that is resistance to flow is added. So, the skin friction effects increase and the mass flow rate is dropping, but simultaneously, because you are adding more fins, the surface area is increasing. Initially, when there was lesser fins, surface area was not sufficient to dissipate the heat that was conducted to the fin. It has to be dissipated into the air flowing medium. So, that surface area if it was limiting, then the resistance was high. As we add more surface area, the mass flow rate is dropping, but that is still sufficient to dissipate, because what is required is that there are two parts to this, is that the convective heat transfer, that is HA component, should be balanced by m dot Cp component. M dot Cp is the sensible heat rise of air flowing through the medium. So, if there is only sufficient mass flow rate, then it can dissipate the Q that is coming from the surface area. So, HA and m dot Cp should be balanced in a heat sink design. So, you can see that as I add more surface area, resistance is dropping, but notice that I do not have a graph here, but mass flow rate will drop because my surface area increase will concomitantly increase the pressure generating force, that is the mass flow rate will go, because pressure generating force is constant or the pressure drop is constant. So, the mass flow rate will go down. So, eventually it comes to a point where the surface area is high enough to dissipate lot of heat, that is the resistance, because the Q is dropping or Q is increasing here, and the resistance is dropping because my T base is fixed to a constant, T ambient is fixed, only this fellow is increasing as I increase more fins here. But at this point, the mass flow rate has dropped so much that as I increase more fins, the mass flow rate is not able to pick up the heat that the fin is delivering it. So, the surface resistance, the overall resistance of the heat sink increases, and this is true even more predominant in the case where there is a bypass. So, what happens is, as I add more fins, the pressure the mass flow rate drops and there is more bypass happening, and as you can see, as you go more, add more and more, eventually mass flow rate drops inside the heat sink, that it cannot take more fins, and the minimum resistance is much higher in fact compared to the no bypass case. So, it is always better to have a no bypass case, but manufacturing tolerances and others dictate that there is at least some limit, some tolerance or some gap is always there on top of many of the packages. And moving forward with this, now this is the heat sink arrangement, and you can see there are many different types of heat sinks. So, how do I measure longitudinal, active, when there is a fan that is fin, foam? So many different types of heat sinks are there. These are examples from actual processor. This is a processor pin. These are line grid arrays. The variety of processors, these are pulled out of a computer in the lab, and this is a radial fin where heat is being dissipated into this pocket and dissipated where there is a fan on top of it, and it is blowing down and heat is dissipated from this. So, you see a variety of fin configuration. How can we judge? And this can be, these are heat sinks, but one can take examples of heat exchangers as well. When is a mechanism or a added surface element or surface area is going to be useful to you is a question. We typically in conduction heat transfer, we talk in terms of effectiveness of a fin, but in a heat sink, what or heat exchanger, what is the way to look into it? is the question. So many classifications, so many ideas are there, and we will discuss first this idea of how to judge heat transfer enhancement, and we go back to the reference from Webb and Eckert back in IJHMT, the International Journal of Heat and Mass Transfer, page number 1647. So, we want to look at rough tubes. Rough here means some surface area element is added to the tube. This is, we are going to look at a tube fin heat exchanger, for example, which is very common in many industries. And as we, if we take a smooth tube and then add some roughness or heat transfer area to improve its heat transfer coefficient, we know that adding a heat transfer area, surface area, because surface area increases, heat transfer will increase, but concomitantly the friction factor or friction also increases, fluid friction also increases. So, there is always a trade off. So, one, we will look into three conditions where we will judge whether added roughness element is useful or not going to be useful. The first is the reduced heat transfer area for equal heat exchange. If I added a certain extra area, can I decrease the length of my tube, for example, so that I have the same heat exchange as before and the same friction factor as before, or frictional power loss or fan power or liquid pump power, because this is talking about compactness. Can I compact my existing heat exchanger if I were to add some extra surface area? Then the second situation is increased heat exchange. This is, I keep the same length or something, I keep the same volume, but I increase the surface area in there. Will I increase my heat exchanger capability? This could be applicable equally for heat sinks as well. The last part is, can I reduce the friction power for equal transfer of heat? So, all these three cases we are going to take up, and this is coming from this reference. So, the main ratios of interest is that we refer to R for rough tubes and S for smooth tubes. Rough, and this is for smooth. Kr is the conductance. Conductance K here is nothing but heat transfer coefficient times surface area. This K is the conductance, convective conductance, and P, capital P here refers to the pumping power. We will discuss pumping power in a short, which is nothing but the flow rate times the pressure drop across it. So, pumping power. So, we are interested in understanding these ratios, and if these ratios, if area, if conductance is higher, lower, pumping power, these are the quantities of interest or parameters that we have, that we can vary and try to figure out whether the device, the enhancement device, the heat transfer enhancement device is useful or just a waste of effort. So, let us start with this, assuming constant properties, that is, there is no dependence on temperature, and we will just ignore the pressure and temperature dependence of the properties and just assume them to be constant. And as we discussed, the ratio of conduction, convective conductance is nothing but HA of the rough tube divided by HA of the smooth. We can manipulate this expression and obtain a more non-dimensional expression, that is of more value addition, is to say that the conductance ratio can be written in terms of HA of rough tube by smooth tube. We divide and multiply by rho. Rho is the density, Cp is the specific heat at constant pressure, Vr and Vs, these are the volumes of, velocities of the flow that is happening in the rough tube. There is a flow velocity in the smooth tube. So, we multiply and divide the same factors and group them into Stanton number. St is the Stanton number, which is heat transfer coefficient divided by rho Cp into velocity, and G is the mass flux. G is the mass flux, which defines the Reynolds number or the mass flow rate into the device, rho into V, and AR is the ratio, surface area ratio, that we are interested. And pumping power, as I discussed, Q here is not heat transfer rate, this is volume flow rate. Which is in meter cube per second. And now we have all the definitions done. We will move forward, and we know for a rough pipe, we know my volume flow rate is velocity of my velocity going through the rough tube times the cross sectional area, and pressure drop we can define in terms of friction factor, the fanning friction factor, and we get this expression for pressure drop. So, how do I use? We can use the existing correlations and so on. Now, we take this friction pressure drop and plug it into the volume flow rate. We know we plug it into the pumping power, which is pumping power we defined as this. So, we have the expression for delta P, we have the expression for volume flow rate, we plug that in and we get this expression for pumping power. F is the fanning friction factor. So, then we define a hydraulic diameter, which is typically known by L by dH, and this definition uses, and we can get AR is the surface area of the roughness, surface area of the rough tube divided by 4 times cross sectional area. We take this 6 and substitute it in 5, and we gather them in terms of GR, FR and AR. So, we get this expression number 7. Similarly, we can find the ratio. We can find the ratio of PR divided by PS. This is the pumping power ratio divided for the rough tube divided by the smooth tube. It turns out to be a factor of friction factor ratio, area ratio, and cubic independence on the mass flux. What is mass flux? As we is rho into velocity. As we move forward, we can also rewrite the previous expression in terms of mass flux, because this is more important to know mass flux, because with mass flux we can calculate Nusselt number and so on, pressure drop. Both mass flow rate is required to calculate both friction factor and the Nusselt number. So, we rewrite the expression in terms of the mass flux ratios. Similarly, we use this expression in equation 2 and write the convective conductance or conductance ratio as this, and you get a beautiful expression in terms of Stanton number ratio of rough tube divided by Stanton number ratio of smooth tube divided by 1/3 of the friction factor ratio. So, often experimentally or numerically we can determine the Nusselt numbers for a rough pipe, and we know that for a rough pipe the correlations are existing for friction factors, Petuko or anything that can be used. So, Dittus-Boelter is something if you are in the turbulent regime, and this is the Blasius relationship. So, assuming that we know how to quantify the rough tube heat transfer coefficient and Blasius solution, we will start with the assumption, or the first assumption, which is the constant pumping power case and constant area case. This is that both smooth tube and rough tube have the same area, and the pumping power is also fixed constant. So, the goal is to see whether this enhancement is going to fetch us compactness. So, we move forward and we plug using the relationship so far obtained in here. We know PR is by PS is constant, so it is equal to 1. So, we get an expression called this, which is friction factor times the mass flux ratio of the rough tube or raised to the power cube, and smooth times this. Similarly, the conductance ratio stays the same, and so we know, usually we know the Stanton number and the friction factor for smooth tubes is well established. So, now we have all the expressions, and if Kr by Ks is, we know all these factors. So, if we put it and if it is greater than 1, then we know conductance of the rough tube is higher. Therefore, it is useful. What we see is that because the constant pumping power and area is fixed, the rough tube now is, if we obtain a relation where Kr, which is the convective conductance ratio, is greater than 1, that means my device is able to deliver more heat transfer. That means I can achieve compactness with this device because my area is also fixed. So, I can go to a smaller area, and with this enhanced heat transfer rate I can obtain that. You can manipulate the expression, you will see that it is only a ratio of heat transfer coefficient of R divided by Hs. So, putting this and so on. So, you get to see that with this expression, this expression of. So, we see that with this expression that we discussed, we get a heat transfer coefficient ratio, and this expression gives us a very good assessment of whether the proposed enhancement scheme is going to work for you or not. And so, that is why we can use that as a criteria for judging if the constant pumping power per area. Similar ideas can be developed if we keep the next one, which is constant pumping power is fixed and the conductance is also fixed. My Kr by K smooth is also equal to constant. In such situation, now I can calculate what is my smooth to rough surface area ratio, and again come back and adjudge that this is going to be purely a function of the surface area. The conductance is going to be only a function of surface area, and the mass flux ratio is going to be of this form. With all these three expressions, now if my AR by AS is less than 1, then the roughness element will provide compactness. So, I can see that I can use the same set of expressions and determine even what compactness or what difference we need, we can get it. And the last part is that if we keep the constant area and conductance same, whether can we reduce the pumping power. If the same expressions can be used, and here if pumping power ratio PR by PS is less than 1, then the enhancement scheme is worth pursuing for lower pumping power, and that is it. With this discussion, we can see that we are able to manipulate the expressions in terms of conductance ratio and so on, and adjudge whether the device is going to fetch you an enhancement scheme is going to work for you or not in terms of either size reduction or improvement in heat transfer rate or decrease in pressure, the pumping power.